Okay, welcome back to part 2 of our overview of using GLHEPRO. And again, this is just an overview to explain the sort of general flow of work, generally sort of maybe the main ideas behind how it works. And my plan is to create some additional videos to cover various aspects of it, but that'll be in the future. Okay, so this is the main screen of GLHEPRO, and this button, the little, let's see here. This button here, or these two buttons here, allow us to specify the loads. And we're going to come back to those, the loads we just did at the end of part 1. We're going to press this button and put those in, but that slide comes up somewhat later. So, okay, these 3 buttons here run either a simulation. A traditional monthly simulation is the first one. It can also run an hourly simulation or a standard sizing procedure. All right, and yeah, I guess I just realized this box actually should include the hybrid sizing here. Hadn't noticed that, but it should include that. These 4 buttons can do simulate, sizing, or hybrid sizing, and it can do an hourly simulation. So this button is used to select the sort of number and arrangement of the boreholes. So we can, in this particular case, we've already selected a rectangular 2x2, but we can actually have quite large boreholes, like 20 by 45 or something like that. Go up to 990 boreholes right now. This button that says calculate borehole thermal resistance, it actually does a bit more than just calculate the resistance. It also calculates what we call the short time step G function, which controls how the ground heat exchanger reacts over a period of hours to changes in the input, or changes in the load. Okay, you can set the flow rate and the antifreeze type, or if it's just pure water, by selecting the fluid. You also select the temperature at which you evaluate the properties. So generally speaking, that should be done for what you anticipate the peak condition. So if this were a heating case, this would be the flow rate for design conditions and heating. This would be the temperature we anticipate achieving. So then, and we'd be using this ethanol water 26%. And then we would use properties in the simulation that are shown here that are appropriate for those conditions. All right, and we can then select a heat pump, or probably more likely specify one. We have a library of heat pumps. It's very hard for me to keep these up, so GLHEPRO 5 came out in 2016, and these were, I would say, up to date then, but of course there's a lot of new heat pumps on the market, and some of the ones in the library are no longer on the market. So, but it's not too hard to specify. The ground properties can be set here. You can actually use there's a library of ground parameters. It's fairly small. Also a large database for ground temperatures, and I can explain that later how that works, but we basically set the ground properties and also the temperature, undisturbed ground temperature. We also have the capability, though it's not used for most vertical boreholes, of accounting for temperature change over time of the ground. So we do have a feature to do hybrid horizontal systems, and in which case then these variations in the ground temperature can be usually not super important, but they can make a difference, so we can account for that. Okay, borehole dimensions are set here. The borehole depth can be found with the size routine. You can also just put in a number and simulate the system and find out what temperatures you can expect. We've got the borehole diameter here, the borehole thermal resistance, which is calculated with this utility here, and then the spacing between the boreholes. Okay, so I mentioned you can choose from a fairly large number. There's a set of library configurations. This is just the start. They go up to, I think, 12 by 10. And then there's an option called 990 where we actually, you specify, say, a minimum of 10 in one dimension and a maximum of 99 in the other, somewhere up to 990 boreholes. Let's see, did I lose a note? Maybe, I think yeah, apparently I got my animation messed up. So this is the borehole resistance calculator. It also calculates a short time step G function. It also has the feature to export the entire G function to a file where it can be used by a simulation tool like Energy Plus. So let's see, if we start here, the Reynolds number is calculated based on the fluid type, the concentration, this temperature, and the flow rate. And it takes all those things into account and calculates the Reynolds number. It's also possible, if you'd rather, you can enter a convection coefficient. You can account for short circuiting in the borehole. So I have another lecture where I discuss that on the introduction to modeling of ground heat exchangers. Has some discussion of short circuiting effects. And then I plan to make some more specifically to GLHEPRO. And for short circuiting, there's two different models. These were developed by Yor and Hellström in Sweden, and we often just use the mean value of the two effects. If we calculate the borehole resistance, it calculates the resistance, it puts it there. It calculates the Reynolds number and puts it there so you can see if it's likely to be turbulent or not. We can export the G function to a file with this button. And also we can, most boreholes in the US are filled with grout, like bentonite clay, quartz sand mixture, for example. There's also cementitious grouts, or there's bentonite grouts that are unenhanced, or bentonite grouts enhanced with carbon particles. In Europe, or specifically in Scandinavia, I say Norway, Sweden, and Finland, it's quite common to use boreholes that are groundwater filled. We can also model that at least for the single U-tube case. And we can model a U-tube, single U-tube, a double U-tube, concentric heat exchanger, and standing column wells. So those are all additional options, though. This is what you're looking at here is just the single U-tube. Okay, the heat pump. This would be an example where you're selecting one. If you have to add one, you actually add data about at different temperatures. You give it the how much heat or say how much cooling is being provided at that temperature, or what the cooling capacity is, and how much heat is being rejected. And it will figure out a curve, and that's what you see, this A plus B times EFT plus C times EFT squared. It can figure out a ratio of heat rejected to the cooling provided, or the power to cooling provided. It'll estimate the energy used by the system. And it does the same thing for heating. And, well, there's more features, but we'll come back to those later. Okay, and as I mentioned, you can select the antifreeze properties. You basically specify the constant type of antifreeze, the concentration. And then there's also the possibility for library. So in terms of mixtures, we have sort of built in, you have ethanol, methanol, ethyl alcohol, methyl alcohol, propylene glycol, ethylene glycol. and water mixtures, but if you use some other kind of brine, it's possible to put it in a library and use those values. Yeah, complete property formulations for that. You know, if you use some other sort of brine, you can actually enter data for it in the library. Okay, so in part one we left off, we got the loads with the spreadsheet, that's the peak load analysis tool. If you come here and you say paste, it will take those 48 values, the 12 months, 4 values, it'll paste those in. You have to manually tell it the number of peak hours, heating hours, and cooling hours that you want to use. Yeah, so, and yeah, the durations are manually entered. Okay, so GLHEPRO, it does support simulations with Energy Plus. It supports, maybe I should say supported simulations with HVAC-Sim Plus. We used to do a fair amount of simulations with HVAC-Sim Plus and don't use it so much anymore, but it can output the G function in a form that could be read, at least by our HVAC-Sim Plus interface. It also has a standalone simulation that you can use to simulate a system in GLHEPRO itself. It can be used to design hybrid systems. We have our own methodology for that. So that would be a system, say, with a cooling tower, for example. You can enter direct the heat exchanger loads. We talked about that in part one. And so I used the example actually there of using, quote, free cooling with a fan coil, where we're just circulating fluid directly from the ground loop through the fan coil unit. I showed you a library. I showed you the possibility, or I didn't show you, I told you could also, take rectangular cases up to 10 by 99 boreholes. So we also have another feature for irregular borehole configurations. The user you can actually specify up to 36 boreholes. You can specify the position of every single borehole. So if you have a banana-shaped field, you can specify that. You can make the boreholes. They can be vertical. They can be inclined. They can even be different depths. Although I would say the simulation doesn't take that into account in every respect. It doesn't have any way to recognize that if you have different depths of boreholes, they may have different flows. It's not that sophisticated. We can model horizontal ground heat exchangers straight, straight in a line heat exchangers or slinky heat exchangers. So it has quite a few features. Good question is, okay, yes, you have all this, but does it work? So we've done some validation. You may notice our example, like I showed you, I think a 10-year example. We often sized at 20 years, 25 years. There are no data sets that I'm aware of that extend to 20 years. And there may be some other data sets now, but about 5 years ago or so, this was all that we could find. So we had run a system with 3 boreholes here for 19 months. The ASHRAE headquarters building had 12 boreholes, and it had run for 55 months. We had 55 months worth of data. There's a system in Valencia, Spain, that at the time we had about 6 years. I think there may be 12 years now, but it is only 6 boreholes. And why do I say only 6 or only 3? In a system with only 3 or 6, there's not a lot of opportunity for long-term heat buildup or drawdown, right? So you don't necessarily see every effect that GLHEPRO can predict, right? And that's actually, it's also true of the Atlanta and Leicester buildings, that they're reasonably balanced for heating and cooling, so we don't have really good evidence for, say, long-term heat buildup. I don't say we don't have evidence in the form of data sets where we have, good quality data. There's certainly anecdotal evidence of systems that build up heat over time. It's just that we don't have good measurements for those systems. But if a viewer has good data, I'd be very interested in hearing from you. Okay, so this was the work of my James Cullen, my PhD student. And what we did is we tried to validate the design tool by taking these 4 systems, and for each system using the actual ground thermal properties and using the actual heating and cooling loads that were measured, going through the workflow with GLHEPRO and saying, okay, what size would this have to be? How deep would it have to be? So, only specifying for still water the 3 boreholes and the distance apart, right? And then if we use GLHEPRO and said, oh, we have a 19-month design period, what size would we have to achieve? We also used the, quote, hand method in the ASHRAE handbook. And then we sort of handicapped GLHEPRO with simplifications to make it more like the handbook method. You can't perfectly match it, but you can sort of partway match what's going on in the handbook method. That's what we tried to do. So this is, again, James Cullen's PhD work. The blue is what the system actually has in terms of borehole depth. The red is what we get with the handbook model. And you see there's quite a bit of difference between the blue and the red for a couple of the cases. For other 2, Atlanta and Stillwater, it's not that far off. There's no specific trend, and for Valencia and Leicester, we get higher predictions by the handbook than actually exist. For Atlanta, we get a lower prediction. For Stillwater, we get a little bit higher prediction. Okay, then we have the design tool, which we got remarkably good results. And then we took the loads and loaded them the way the handbook treats it. And you can see, if you go from the green to the purple, then look back at the red, you see, well, we went part way to what the design tool's doing. Although for Atlanta, right, it didn't make that much, well, I'm sorry, for Atlanta, it actually got us quite close to the handbook method. And for Stillwater, we went from this with the design tool, with the loading used for the handbook, we actually went further from the handbook. And then if we use the borehole thermal resistance method that's described in the handbook, we get these yellow values, and they may also partly correct the value, getting it closer to actual, though Atlantic goes the opposite direction. Stillwater goes the opposite direction. So I won't say it's completely conclusive. The handbook method makes more simplifications than GLHEPRO. And there's a lot of research that's gone into GLHEPRO, which has been published, and so is available in the public domain. I will talk about that some in some other lectures. Okay, there's 3 studies altogether that give uncertainties in design when the loads are known. Right, so the study just discussed, we got within about plus minus 5%. James Cullen also worked on another study looking at, for a wider range of cases, the effect of using this monthly peak load. That's about, we found that to be about plus minus 8%. And then I did some work with Saqib Javid, who's at the University of Lund and Chalmers universities in Sweden. We looked at this effect of uncertainty in the thermal response test results. And that suggests about a plus minus 10%. In other words, how well we know the ground thermal properties, even when we measure it, suggests that there's uncertainty in the final results about plus minus 10%. So that suggests a safety factor of 10% isn't unreasonable. But in fact, there's also the uncertainty of the loads. So in this study, we measured the loads, but when you're designing a ground heat exchanger, usually, you don't know the loads in advance. So that's another possible reason for suggesting some safety factor. The flip side of that is that ground heat exchangers tend to be fairly stable, and so um, and usually the system isn't, when we choose a design entering fluid temperature, it's usually not the case that the system fails if we exceed it by a degree. So all these things go together in maybe deciding on a final safety factor. Okay, finally, here's some references for some of the things that I mentioned in the presentation. Some of these papers, like this ASHRAE transactions paper, should be available on our website. Others are available through sort of normal academic channels. So, thanks.